let's get started. Hello. Good, thank you. Hi. So, welcome to the summer seminar series. Today's speaker is Hector Socas Navarro. He's a good friend of mine, so it's kind of weird to introduce him. But anyway, Hector studied and did his PhD at La Laguna University in the ISE in the Canary Islands. Then he moved here for his first job after that. He came here as an associate scientist in 1999, I believe. Then he was reclassified as a project scientist and then as a ladder track scientist, and he ended up leaving in 2008. So I overlapped with him here for about a year and a half only. He went back to the Canary Islands because he got a permanent position as a scientist at the Astrophysical Institute there, where he still is and presumably will be for a long time. It's also his home, I was going to say town, his home island. So I'm assuming he's very happy there. But he is an affiliate scientist of HAO, so we get to see him every now and again. He's actually here for a month now, working with me, with Alfred. We're going to be working together with Anna Grignon, who is our combined PhD student, who's going to, I think she's arriving tonight. She's
arriving this evening, yes.
She's coming for 2 weeks. With that, I'm just going to leave him to it. Not a very good introduction, but he can introduce himself.
Thank you. No, it was a great introduction. Thank you, Rebecca. It's great to be back here, see so many old friends here in the audience. Thank you for coming. So, like Rebecca said, the first time I came here was back in 1999. I actually came for a visit in March before I finished my PhD. That was 15 years ago. It's amazing how much everything has changed, except you all. I mean, you all look great. You all look the same. HAO has changed a lot. This is what HAO used to look like back then. We were at the Foothills lab, and this is what I used to look like back then. So, no comments, please. And it's interesting. One of the first things that I heard Tom Bogdan told me when he was hosting my visit was about this curse of the Boulder Valley. And apparently this was a curse that is attributed to Chief Niawat, according to which him who looks upon the Boulder Valley will never want to leave. And so for that reason, I am very thankful to the people who have made possible for me to be back here. So I want to thank HAO, the Visitor Committee, Ganglu, the Affiliate Scientist Program for supporting my visit, and also support from my home institute, the IAC, and the Severo Ochoa Excellence Program, which is an excellence program for excellent research institutions to support excellent scientists to do excellent science. So I'm very happy that they think I'm an excellent scientist and that my visit here will be a contribution to excellent science. So yeah, thanks. This is a 1-month visit. I'm halfway through it, so I have like almost 3 more weeks to go. So please come by and talk to me. I'll be happy to talk to each one of you. My office is upstairs on the east side of the building, facing the highway. And yeah, please come by. So, of course, we're going to be talking mostly about the sun here. And I'm probably preaching to the choir. I don't need to spend much time on this slide. But these are the 3 reasons why I think studying the sun is so important nowadays. First of all, the solar cycle impacts our society, our daily lives. You all know this. But also, it's very important to understand other stars. We are very interested in astrophysics, and the sun is our Rosetta Stone for other stars. We learn about stellar structure, evolution, about dynamo mechanisms. We learn all that basically from the sun, and then apply it to other stars. But also there's another very important reason, practical reason to study the sun, and it has to do with the fact that it's an exceptional laboratory where we can learn about physical processes that we are not able to replicate in the lab because we cannot reproduce those conditions, and not even on numerical simulations. We still can't produce numerical simulations with the properties of the sun. And very important, we are now in order to harness fusion, nuclear fusion energy, which is very important because we're in this race to either destroy our world or develop fusion energy, whatever comes first. So hopefully we'll get there first. And so solar physics is important in this context, not only because the sun feeds from fusion energy, but also because the only way we've found to make this feasible is by confining the plasma that we're going to fuse or whatever. The plasma that we're going to burn, we confine it with magnetic fields because we don't have any other container that can sustain those temperatures. And you know, very hot plasma confined in magnetic fields. Where can you observe that? Well, obviously in the sun. So that's a very important reason because all the plasma physics that we learn in the sun has that that application. And then, yeah, just put these three pictures here to show you that there's a lot of interest in solar physics nowadays. These are probably the three biggest projects that we have going on. These are projects of several hundreds, millions of dollars, and we are embarking these really big projects. So even the funding agencies realize that solar physics is important. And another reason why I am posting these pictures here, DKIST, sorry, the European Solar Telescope. This is a representation of Solar C. It's actually Hinode. You've recognized it, but there's not even a conceptual design of Solar C yet, so there's nothing to show there. That's a placeholder, but it's moving forward. It's happening. And the other reason I want to show this is because these three projects have one thing in common, and it's that chromospheric magnetometry is a big priority in all three of them. And I'm going to be talking a lot about chromospheric magnetometry. So then the second question is, why the chromosphere? What's so interesting about the chromosphere? Well, to begin with, the chromosphere is a fascinating transition region where we go from the a regime in the photosphere where it's the gas pressure that dominates the dynamics to another region in the corona where it's the magnetic field that dominates. And in the middle we have this weird place where none of these two extreme regimes apply. So you have all sort of weird interactions that produce crazy things that we just don't understand. So this is an example. This is a movie taken with the Swedish tower. This is actually H alpha. You can see here a sunspot and all these spikes that come out of it and seems to be breathing up and down over time. And you see different things at different wavelengths. So we don't understand any of this. You could stare at these movies for hours, and they are very pretty. I mean, you see some things that illuminate from time to time, and we think that might have something to do with reconnection. We see these dark clouds moving in towards the spot. We have no idea what that is or why it's doing that. But another reason is because we more or less are able now to measure more or less routinely the magnetic field in the photosphere. But that's just one very thin layer. And we've realized that we need to know what is the three-dimensional structure of that field. We need more perspective. So we need to have measurements at other heights in order to try to at least have an idea of what this magnetic field looks like in 3 dimensions. Of course, going down is almost impossible. It's easier to look at higher layers, like the chromosphere, where we are starting to be able to make some measurements like that. And finally, another reason is that we are at a point where the observations of the chromosphere are starting to be sufficiently abundant, and we are starting to know enough about their interpretation that we can actually make progress. So we're at the point where the chromosphere, it's difficult but doable, right? So that's the interesting regime in science, where you can make progress, you can make advancements, but it's difficult, and that's why it hasn't been done before. At the same time, simulations are starting to be fairly well developed about the photosphere. I mean, Matthias is able to simulate sunspots even. But in the chromosphere, we are starting to have the first simulations. It's still very, I don't want to say preliminary, it's very interesting work. But yeah, it's still work that I think is pioneering in many respects. So there are still simulations of very quiet regions, and they don't account for all the physics that's in there, but at least there is something that we can start comparing with observations. So also, it's interesting from that point of view. Now, So we don't want to have just movies like the ones I show you. Those are very interesting, but what we really want to have is we want to have polarimetry, so we know what the magnetic field is doing. Like you can see here, these are calcium infrared images, also from the Swedish tower. This is a movie of a sunspot again, but this is, now you can see intensity and polarization. These are two orthogonal linear polarization states, and this circular polarization. And you can see that there's also a lot of stuff going on there. And it's interesting because the polarization is what helps us sort of measure the magnetic field. So that's why we want to have it. And when we make these kind of observations, we are, of course, looking at a single wavelength. This is a very narrow filter, a very narrow bandwidth, next to the core of the line. In this case, it's a 8542 angstrom line. And the closer you get to the core of the line, the higher you see in the atmosphere. The further you go to the wings, the lower you see down to the photosphere. But again, what we really want to have is the full profile of the line. So eventually, we want to build data cubes where we have x, y, lambda, and then how that evolves with time. We really need all that information. And you can already, well, this is just a scan through the line where you can see how what you're seeing changes from the core of the line, where you see the highest layers, to the wing, where you basically see the photosphere. And we want to have all that information to be able to reconstruct the atmosphere in height. So it's a lot of data, I think, is the message I'm trying to send here. So we have all these pixels here. For each one of these pixels, we want to have the spectrum in that pixel, and we want to have polarimetry, and we also want to have time sequences of that. And that's very hard to capture because our detectors are two-dimensional, right? Just like our eyes. So you can either scan a slate over this field of view, and then you lose some spatial coherence, or you have an instrument that captures the entire field of view at the wavelength, and then you scan those wavelengths. Either way, you lose some coherence there, either in the spectral direction or in one of the spatial directions, because you have this limitation that everything is 2D. So that's part of the challenge there. But anyway, whatever you do, you end up with massive data sets. And that's why you're going to hear me a lot talking in this presentation about efficient methods, about parallelization, about using supercomputers. And the reason is that we have enormous data volumes. And I think, in fact, that it is not possible to approach this thinking that you're going to process everything, do inversions of all your data. I think we're going to have to be selective. We're going to have to think a little bit about what we want to do, and yeah, try to be a little clever about what data sets we want to invert and in what conditions. So either way, the situation that you have is that we have models of both the photosphere and the chromosphere now. We have observations, and we want to bring those two together, right? And that's where NICOLE, which is the code that I'm going to be talking about today, is useful because it allows you to bridge this gap between the simulations and the observations, right? So it allows you to take a simulation data cube, like I said, from the photosphere or the chromosphere, and then synthesize spectral profiles. You can compute the spectral profiles of chromospheric lines, photospheric lines, anything you want, with polarization. And then you can compare that to your observations. Or the other way around, you can take your observations and perform inversions on those observations to retrieve the physical conditions in the atmosphere. And then you can see if those physical conditions you're able to understand, and maybe if they look anything like what you have in the simulations. So that's why I think it's important to have a tool like that that allows you to bridge this gap. So now that's a reference to Big Bang Theory. Where they're playing rock, paper, scissors, and they realized that that game was too trivial, and they made it more complicated by adding Spock, like Star Trek, the Spock character, and later on they came up with a more complicated game. So basically, there's three key elements, which in this case are simulation, observations, and synthesis, and then you realize that yeah, you need more elements in there. So anyway, it's a bad joke. Sorry. I was hoping it would go unnoticed. Anyway, so that's interesting. People are actually paying attention, so I need to be careful what I say. Okay, the title of this talk is actually pretty long, and it's not something you should do. I've been told that you have to have very short, precise, concise talks for your titles for your presentation. But I did that on purpose because each part of the talk means something. So it says NICOLE, it's an open source code, and what that means is that we view it as a community project. So it's something that we start. We put in the initial effort to get some good starting points, solid foundations, and then we're going to put it out there for others to hopefully take that and maybe expand on it, improve it, or I don't know, modify, adjust it to other applications. So the code is hosted at GitHub. You can download it from here. Right now it's officially a beta test, but we are going to make it officially public when the paper comes out. We are writing the paper. The first draft is almost complete now, so I expect we will be submitting it in a few weeks. So at that point, then this will be officially marked as a version 1.0, public version 1.0 of NICOLE. But anyway, so you can already download it from there if you wish. And so people can create their own new branches of the code. Not only we welcome that, but we also encourage it, and I'm happy to support anybody who is interested in doing something like that. It's released under the GNU license, which means that, yeah, you can do whatever you want with it. You can copy it, you can distribute it, take parts of it, anything you want, except that whatever you do with it, it also has to be public and make it available to the community. Okay, the other part of the title, it says that it's a massively parallel code. And the word here, massively, is important. Because actually, so this problem it lends itself to a very simple parallelization, because you can basically send each pixel to an independent processor and then collect all the inputs and all the results. So that's nice. But you have to do it the right way, because when I first started implementing parallelization in NICOLE, I did it in a very naive way, let's say I took some shortcuts. It turns out that the code will work well for I don't know, 10, 20, 50 processors. But then after that, the overhead introduced by the communication between processors and stuff like that will bog down, so that eventually there will be no gain after 40 or 50 processors. So then we improved that. We came up with a better scheme, and now it's a massively parallel code, meaning that it parallelizes. It almost has perfect parallelization up to 1,000 processors, and we've tested it up to 500, and we don't see any signs of saturation. So that seems to be working well. It's a code for synthesis and inversion. This is what I mentioned before of how you go from simulations to observations, or the other way around. And this capability, the inversion part, is particularly unique, especially for the chromosphere, right? Because there's not a lot of inversion codes that can work with chromospheric lines. And at this moment it's a Zeeman effect only. So we don't have Hanle effect, which is kind of a limitation that we don't like to have. But yeah, we're trying to explore ways to have some Hanle effect capabilities in the code. But it's not easy, because it will actually imply that you have to go to full 3D in ONLT, and that's something that we're considering right now. Oh yeah, I forgot to mention my collaborators here are, well, mainly Javier and Basilio, my thesis advisors, because I started working on this during my thesis. And then over the course of the years, I've been able to recruit some more cheap labor, Andres and Jaime, cheap but very highly qualified labor, who have really helped a lot. And they've done a lot of very nice things with the code. So I'm going to describe a little bit how it works. Well, we've put a lot of effort into making it user-friendly. Okay, so it's as user-friendly as it gets. It's got an extensive user manual. It is multi-platform. It's written following strictly Fortran standards, so it should compile on any decent Fortran compiler, Unix, Mac, Windows, anything. We just, the other day, Rebecca and I installed it on Yellowstone, and it compiled without any problems. So that shouldn't be any problem. It has some wrappers that you can run that do the initial configuration of the code. So it scans your system, checks for whether certain nice features are available or not, and then it will use them or not. It can read IDL data files, and I'm thinking maybe in the future to also make it read CDF, not CDF files. It's well documented. It follows when I said it follows the strict ANSI Fortran. It's actually Fortran 2003, although there's very few 2003 features that it uses, and most of them are covered by most Fortran 90 compilers anyway. So most Fortran 90 compilers will be able to compile this code. It's got no common blocks or anything like that. It uses the modular architecture of Fortran 90. Although over time the modules have become a bit fuzzy. So it's not, one of the things I would like to work on is to encapsulate it better so that people can take modules from this code and use it in their own codes. Right now, there's a little bit too much interconnection among the various modules. So that's one thing I want to improve in the future. Memory is allocated dynamically, so you don't need to be, recompiling the code every time you change the size of your atom or your atmosphere or anything like that. And the source code is pretty clean. It's relatively easy to read and modify. And like I said, we put a lot of effort into this because we are expecting, or we are hoping, that some other people will take this code and modify it. And this is one thing I wanted to do from the beginning. I mean, my experience, Fortran and humans should never talk to each other. Okay, it's a horrible, horrible thing when Fortran and humans have to talk to each other. That should never happen. So I've made the Fortran code so that it only reads and writes binary files, and there's sort of an interfacing in Python that does all the communication with the humans, that does the parsing of the configuration files, all of that. And you can do very nice things with Python. It's got such nice high-level features that it makes it very easy for the user to interact with this script. And then this script will basically write all the binary files that the code will need to run. And so the code lives in its own binary universe and doesn't have to interact with humans. Parallelization is implemented using MPI, which is available anywhere, everywhere. And it uses a master-slave scheme. So the way this works is that there's a master process that will read all the data. It will check with the slaves. Whenever a slave is idle, it will send a task to the slave. The slave would do its work and then return the results back to the master. And then all the input-output is handled by the master. So that's very convenient because sometimes some supercomputers have trouble when you have many processors accessing the file system at the same time. That could create problems or at least delays. So we avoided that by having the master deal with all of that. And so the slaves, they only do calculations. That's all they do. Yes. No, because the master reads each column at a time and sends it to a slave. So the whole cube is not being held in memory at the same time. It's read, on a column by column basis. That, of course, might change if we go to 3D in the future.
So in client race, then you're in trouble,
Yeah.
Because then the master has to do all the calculation over each race.
No, what happens, there's a Python program. If you want to incline your model, there's a Python program that does that first. So it takes your cube and inclines the cube, and it produces a fake cube that then the Fortran code works with. So just to give you some numbers, I know this is completely meaningless, but just to give you an idea of the size of this code, it's got almost 30,000 lines of code, over 100,000 words. Almost 6,000 of those lines are comments. Okay, so I think that's a pretty good ratio. I didn't know this until I made these numbers. I'm pretty proud of that. So basically, 1 in every 5 lines of code is a comment or has a comment. That's pretty good. The manual has 84 pages. And it should have more, because over time it has developed into some sort of reference where all the options are explained. But I think it should have more tutorial and more examples or something like that. There are some, but I found from the testers trying to run the code that they sometimes ask me the same questions, and I should probably, maybe do a better job with the manual. So this is work in progress, I guess. Source code distribution is 13 megabytes. It used to be less than 3 megabytes until a few versions ago, but now I've hardwired some data for ultraviolet opacities there, and so it's grown to that size. So that means you cannot email it, but it's still pretty light. The code is multi-platform, as I mentioned. There's a tool that will create automatically a Makefile for you. There's a Python script that you just run it. It will analyze your system and create the optimal Makefile for it. It makes some adjustments, like it checks the endianness of your system. So if you remember, in the old times, you used to have these problems where you have binary files created by a Sun machine or by a PowerPC Mac, and you try to read that on a Linux machine or some PC, and you have to swap bytes. So you wouldn't have to worry about this anymore, because the code that automatically detects if your machine is big or little endian. It will always produce little endian files, regardless what machine you are running it on. Okay, so you don't have to be converting it. The files are always the same. They will have the same structure and the same endianness. There are some test cases. So when you compile the code, you just run the test, and it will go through them, and you can check that the calculations give the results that are expected. You can get detailed profiling information after each run. You get files for each processor specifying how much time the code took to run and how much time was spent in each routine. So that's useful information for optimizing your coding or your execution. And this works both in serial and parallel mode. I forgot to mention, one nice thing is that there's a single branch of the code, and then with a switch, when you configure the code, with a switch you can specify if you want to produce a serial or a parallel build. And so there's very few lines of code that will be altered. There are some defined blocks and things like that, depending on whether you're running on a serial or a parallel implementation. So you don't have to maintain two separate codes for serial and parallel processing. It's the same code with just some, basically the serial version is a version in which you only have one processor, and the master just sends the task to himself. It's got the restart mode in case it gets interrupted. You can just specify a switch, and then it will start from wherever it left off, or crashed. Goodness. And there's also a debug mode where it will spit out a lot of information about everything it's doing on some files. This is an example of one of those profiling files. It tells you the execution time and the most important routines, how many times they were called. For instance, the formal solution was called 18,000 times. It took 0.48 seconds, or 44% of the code execution. So this will help you figure out if it's worth to spend some or to invest some effort trying to optimize something, but maybe you realize it's an insignificant fraction of time that you'll be working on, so then it's not worth to do it. Things like that. So in terms of the physics, like I said, you can run this code in LTE or non-LTE. You can treat blends consistently. You can actually run it in LTE to go faster, but then provide departure coefficients to be read from an external file. So it will be some sort of a corrected LTE run. And it works with complete angle and frequency redistribution. That's an approximation that was necessary for speed and also to make the problem tractable. It's got lots of different options for the formal solution. Normally they all give the same result, but it's nice to have different options in case something strange is happening. You can change that and see what happens. Like I said, it only considers stem and effect, and uses a 1.5 dimension approximation, which is what people say to mean that if you have a 3D data cube, you do the transfer in each column independently. So there's no transfer of radiation between one column and the next. Okay, and that's probably the next upgrade that we're considering, is to go to full 3D, but that's a very, very complicated problem. You can make abundance inversions, and it also allows you to compute lines with hyperfine structure. And let me show you an example. This is a manganese line in the near infrared. You can see it here in the atlas. It has this funny structure, and this is caused by hyperfine structure. And you can see how we can reproduce it fairly well with a quiescent model. We get the same structure that you see in the line. In terms of physics, one of the interesting things that we've been working on is the equation of state. That's one of those problems that are, not really difficult to do, but they require lots of details that you have to take care of, and it can be critical in terms of performance. Because if you want to do everything and everything right, it could take a long time. So we've come up with different approximations that can speed up this process, and to various degrees of approximation, right? So we have several options here that the user can choose from. The first one is the Wittmann-Michalas method, which is the one used by SER, and this is a very popular code that a lot of people use it for the photosphere. So it's a nice option to have, because then you can compare directly with results from SER. We can do the full calculation with 273 molecules to determine, to calculate all the molecules that are there, all the free electrons, so you can solve the full equation of state. But this takes a long time, and more important than that, it's not entirely robust, because you end up with a system of equations of 273 equations, 273 unknowns. Sometimes that doesn't converge. And it's a very small percentage of the cases where it doesn't converge, but when you're computing a 200 by 200 pixel cube, and you're solving that problem lots of times for each depth point, then you're going to run into some situations where this doesn't converge, and that can be a problem. There's another approximation, which is basically restrict that to only two molecules, the two most important, which is hydrogen and carbon monoxide. Or OH, actually. You can choose which molecules you want to use. But so it will go much faster. You still have that problem with stability. It's much more stable, but it's still not perfectly stable. Then there's another innovative approach that we took here, which is to replace that whole calculation with artificial neural networks. And that is extremely fast, but it's only approximate. So you get about a 50% error in the calculation, which sounds terrible, but it's not really that much, because when you're calculating your gas pressure, you're going orders of magnitude, right? So in this plot you have like eight orders of magnitude between the top and the bottom of your atmosphere. So if you're wrong by a 1.5 factor, it's not really that much. If you plot it here, the two curves will go pretty close. But anyway, we've come up with another method which is pretty fast, not as fast as the neural network, but it's pretty fast, and it's extremely accurate, actually. And this is a comparison of the full solution and this method that we've come up with. And you can see that you can barely tell the two lines apart in that plot. So that's very nice. And I'm not going into the details. You can read about it in the paper if you're interested. Background opacities. That's another one of those issues that are easy, but there's a lot of details to take into account. Different people do it differently. You take into account different elements, different approximations. So for the visible, I think it's an easy problem, relatively easy problem, and we have a few options for it. Again, the same opacity package used by SER. Then we have our own opacity package, and then we also include another one by Natasha Shukina. But the problem is that we took Natasha's code, and it turns out that code is impossible to bring it up to modern standards. So we cannot. So we've disabled that code by default, because if you put that in the code, then it's not going to be universal anymore. But the code is there, so if anybody wants to use it for whatever reason, then we probably can find ways to use it. But it's disabled by default to make the code, to ensure that the code will run on any platform. So this is a plot of these background opacities for certain photospheric conditions, and you can see that all three packages basically give the same result, roughly, which is what you would expect. But then the really interesting thing that we have here is in the ultraviolet. This is a big problem, because in the ultraviolet, there's so many contributors to the background opacity. It's a big mess. It's very difficult to do. And actually, I think NICOLE is the first one of these synthesis codes that actually has a decent opacity package. And the reason is that, I mean, you normally don't want to or are not interested in computing ultraviolet lines, but in non-LTE, it could happen that the line you're interested in depends on some other transitions in the ultraviolet. So that's why you need to have your ultraviolet opacities right, because if not, then it could screw your whole calculation. So we have two options in the code. One of them is an approximation by these two gentlemen here, who came up with some polynomial approximants to some of the major contributors to the UV opacity, and that works reasonably well in most situations. But another thing that we did is that, I don't know if you've heard about the Iron project and the Opacity project. These are two really big projects with lots of resources, lots of people working on them to try to compile all the available data in the literature about opacities, photoionization cross-sections, mostly, for most relevant elements, for most transitions, from any level in silicon to silicon 2, for instance. They've compiled lots and lots of data about those elements, and in fact, they've merged these two projects. And so there's a huge database that they have online where you can access with a web form where you specify the element you're interested in, you filter the levels that you want to, for which you want your photoionization cross-sections, and then you submit the query, and they will provide you a file with all these cross-sections as a function of wavelength. So I wrote a script in Python that will basically go to this website and start making queries about all the elements, only first and second ionization stages, and compile all that information. And so all of that is now included in NICOLE. And you can see the results here, or some results. Of course, this is only for a particular case, particular temperature, electron pressure, density. If you change the conditions, everything's going to change. But what this is showing you here is in the ultraviolet. This is in nanometers, the scale. The solid line shows the total opacity, and the dashed line shows the contribution from carbon, magnesium, aluminum, silicon, sulfur, and iron, which are often quoted as the most important contributors. So you can see, well, and all of them also include hydrogen. Okay, this is hydrogen. Yeah, so you can see that it's very difficult to really just pick one, because some of them are relevant in some regions, but not in others. Some of them will provide peaks. And also, you can see that there's a lot of peaks there, right? So approximating this by polynomials, it's sometimes not very accurate. But yeah, we can do it in this way. You can see here, interesting, for example, that the iron doesn't contribute anything in any of the ranges, surprisingly. But there are other conditions in which iron becomes a major contributor. So it all depends on the conditions. So you need to compute that.
Those peaks are bound free transitions.
Yes, resonance transition. And so, but the nice thing is that it might look like this is going to slow down the code enormously, but it doesn't, because we've taken, for each one of those transitions, we created the photoionization cross-section and put it on the grid that basically spans the whole UV region with 1 angstrom steps. And so everything is preloaded in memory. And so when you have to compute one of these things, you just have to go to the wavelength you're interested in. That wavelength is just an index in your matrix, and then go through all the elements and add all these contributions. Okay. So it only adds a little bit of overhead at the beginning of your calculation. You have to read all these tables, but then after that, it's very, very fast. Yeah. I don't understand it either. But no, those are bound-free transients. They're photoionization, yeah. Because it's not the outermost electron that you're ionizing here. So these are transitions from any level. It could be way inside the shell of the atom there, and so there are resonances for specific transitions. Yeah, I don't understand it very well either, but that's how it works. Anyway, so those are some relevant details about the code. Maybe some of the features that make it unique in a way. But the really important thing here is, does it work? And when you talk, especially when you talk about inversions, I still find myself having to answer this question: does it work? Because a lot of people still have these misconceptions. Probably from the 80s and maybe before, that first of all, you cannot do inversions of spectral lines, and I think in part it's also our fault because we shouldn't be using the word inversion, right? I mean, mathematically, the word inversion has a meaning and has some connotations. What we are doing here is actually nonlinear modeling. We're fitting data, which is kind of a different concept. But anyway, it's a bit of abusing the language. And but anyway, and so some of the common complaints are actually things that people used to complain about before the photospheric inversions became mainstream. There were lots of concerns about that. Then I think it became clear that yes, you can do inversions about the photosphere. And now we're starting to hear those same arguments about the chromosphere. And in fact, I remember since when I started my thesis, some people approached me and advised me to not take that project because everybody knows that you cannot make inversions of chromospheric lines. And there are different reasons for that. The three most frequent cases that people make is that, well, the chromosphere is extremely dynamic and it's very heterogeneous. So you cannot reproduce the chromosphere with a single model. And that is absolutely correct. But I think when people ask that question, they're thinking in terms of, like in the 80s where we have these 1D models. We were trying to describe the solar atmosphere with a 1D model like HSRA or VAL-C. But that's not how we work with these things. We are going pixel by pixel, right? We have observations with spectral resolution, and we want to do the inversion at each pixel. And so the assumption there will be that inside the pixel, the atmosphere is reasonably homogeneous, okay? So, and then if it's not, then that means you need higher resolution observations, right? But yeah, remember, we're talking about spatially and temporally resolved observations. We're not dealing with an average atmosphere. Another argument is that the radiative transfer is non-local. And yes, of course, it is non-local in the chromosphere. It is non-local in the photosphere. Same reason. Solution is not unique. That is one very frequent complaint. That is correct. You can have sometimes different combinations of parameters that will produce the same profile. But that is true also for photospheric inversions. And that's why you should not use these codes as a black box. You need to know what you're doing. And when you have uniqueness problems, that's basically because you're asking too many questions to the observations that you have, right? So you have some observations and you have some parameters that you want to constrain with those observations. If you have a relatively limited number of parameters that are well constrained by those observations, you will not have uniqueness issues. If you ask too many questions, you have too much freedom, you have too many parameters, and you don't have sufficient observables to constrain those parameters, then of course you're going to run into that problem. But the best way to find out if you're having that problem is experimentation, right? Just run your inversions, try again with different initializations, perturb your model, see what happens. If you converge always to the same solution, that's an indication that your model is well constrained. If not, if your solutions are scattered all over the place, then you have a problem, okay? So to summarize, does it work? The answer is yes, and we can prove it. This is from a paper from 2 years ago where we did some tests about the inversion code in the chromosphere. This is kind of interesting, actually. This might be the first time in history where somebody writes a paper testing a code, and then 2 years later they write a paper about the code. But actually, there were pressing reasons to publish this, because this question about the chromospheric inversions was becoming more and more pressing, and it had to do with this instrument development that I mentioned at the beginning. So what you see here is the result of making an experiment where you take a model of the chromosphere, a numerical simulation of the chromosphere from the Oslo group, computed simulated observations from those, and try to invert those observations. Two things are important here. The simulated observations were computed with different code. Okay, they were computed with multi, and they have more physics than the inversion because they were computed by multi-3D. So the simulated observations take into account 3D effects, which NICOLE doesn't. So this is an interesting test because you're testing your code against a simulated problem which your model cannot reproduce. Okay, so there's more physics in the simulated observations than you have in your code, which is what you have in real life. In real life, the sun has more physics than you have in your computer, always. So it's an interesting experiment. Anyway, so what you can see here to the right is the model itself. Temperature, velocity, a line of sight magnetic field, and horizontal magnetic field, X and Y. And on this other side here, you see the inversion results. And they look fairly similar, right? You see the same structures. Maybe there are some pixels here and there where perhaps it didn't converge well, or there was some issue. But overall, you get a very good description of your original atmosphere in the inversions. And it's interesting because actually the most discrepant part has to do with temperature in the coolest regions. Maybe you can quite see it here on the figure, but if you go to the coolest regions that are surrounded by hot plasma, that's where you have the most discrepancy, and we've traced that down to 3D effects. Because in non-LTE, when you have something hot around you, the illumination, the radiation that comes from it, is going to make your cool atmosphere radiate energy that looks like a warmer, like the one coming from a warmer region. And so that fools the code because the code doesn't have anything about 3D. So there are some 3D effects there in those discrepancies. But still, it's... Yes, it is. Yes. There's a critical size beyond which it doesn't make any difference anymore. So, yeah.
What line did you pick the size?
Oh, this is for calcium 8542. Yeah, it's just one line.
Now what height?
What height, what? This?
This must be some height on that.
Yes, this is a layer between, I remember it in log tau, between log tau minus 4.5 and minus 5.5.
Okay, so above the temperature mean.
Yes, yes. So and there's some more applications that maybe I could discuss, but I'm going to skip. About the photosphere, this is some work I've been doing with the observations. But anyway, I'll skip to the conclusions because there's only 10 minutes for the game to start and to get going. So yeah, basically, the message I want to send is that this is a very powerful tool. I'm really absolutely convinced of that, and we want people to use it. It's very user-friendly, I think, but it is not a black box. So we're happy to help anybody who is interested and wants to get involved, and yeah, even if you want to come to the IAC and learn firsthand or just interact by email, whatever, we're happy to support you if you're interested in using the code. Please don't use it as a black box. Please, if you don't know what you're doing, don't go to conferences saying that this or that doesn't work, because we've had that too. Okay, ask us first. What are you laughing at?
That's on my next conference.
Oh, okay. So there's some new physics in it that we are very happy about, and most importantly, it's free. You can take the code, use it. You don't have to put it as co-authors or even. I mean, of course, we would appreciate a citation to the paper, but that's all. And branching is welcome, so you can take it and use it for your own problems. Thank you very much.
Thank you. So, yes, please.
You have shown your intensities in terms of temperature. those of high root that is intensity is a high power of the temperature. So high root intensity. Errors are minimized.
So you mean this figure here? Yeah. Well, this is just temperature. It's not intensity. It's temperature, because that's what you want to retrieve from the inversion, right? That's your answer. So.
In the visual presentation, the differences aren't seen because the high root of
well, but it. So I think. Yeah. So what you're saying is that I think.
Just compare the intensities.
Yeah, I could compare intensities. Yeah. But the intensities will probably look more similar. No, it will look more discrepant. Yeah, they will look more discrepant. Yeah. But this is what you're actually interested in. I mean, you try to match the intensities because that's your way to this, which is your interesting variable, right? So this is what you want to compare with the original. But I can do that plot for you if you want to see it. Yeah. Yeah. No, it doesn't. Yeah.
If you pick the right wavelength, it might look like that. If you pick the right wavelength.
Not necessarily. It's no.
Not necessarily, but it's better than if you just take the continuum.
Yes, of course, yeah. Of course. No, but what you're saying is true, and in fact, what I mentioned about these cool pockets here and here, they don't look so different here, but they are. If you look at the intensity profiles, you find that you're matching them very well, and yet your temperature is not so close. And I think it's because of this. Well, I think no, we found that it's because of those 3D effects, which NICOLE doesn't consider. So NICOLE thinks that this is warmer than this, because it can match the same intensity with a warmer atmosphere, basically. Yes.
One thing we said at the beginning was it was easier to go up in the atmosphere than to go down, but in fact, if we have the stars to red, so down in the atmosphere, unless you're talking about below
Yeah.
the photosphere. But
Yeah.
That's another way to get the gradient.
Right.
The different direction. Have you played with that now, or is it applicable?
It is. Yeah, it is perfectly applicable. Yeah, you can invert the infrared lines here. Yeah. No, I meant way below that, because it's not such a big difference, right? It's what 100 kilometers at the most between the infrared lines and the. Is it more than that? Yeah, I don't think it's a really big difference. It's not like going 1,000 kilometers up like this is.
Right.
Phil.
Very nice, thank you for doing this thing. Flavor of love and amazing. I just had a comment about. I wanted a question first about how accurately do you think? Because you're one of the few people who've actually done the right thing and tried to compute the curl of the magnetic field in the atmosphere. Right? I mean, that's an amazing. There's some papers you wrote, very, very interesting. And more or less the only one.
So you've read them.
How accurately do you think you can actually compute things like the curl of the derivative in the height direction?
Yeah.
The thing I'm interested in. I mean, is that something that you want to test? Have you tested that against the HAO and things?
No, that is a very interesting question. The problem here is that these simulations, we're trying to use simulations so that we know what the real atmosphere is. And these simulations are still of a very quiet regions, so we don't have a really strong structure. I've never tried to quantify that, but I have quantified the error in the divergence of B in that same paper, which should be 0, right? So I came up with a number that was roughly about 10% of the. So I end up with a divergence of B, which is about 10% of the, maybe a little less than 10%, the total flux, absolute flux in that. So.
But that is also something we're going to encounter where you're maybe not very large differences in height, because you don't want to be going, trying to do, for example, a curve which you've got. I mean, if you do a continuous inversion of continuous height, then you can do this in calculation. But if you're actually doing something where you're doing discrete differences, then that's.
So do it handle a bunch of lines at the same time?
Yeah.
Yeah, that's what you want to do.
Different elements?
Well, yeah, in LTE, yes, as many elements as you want, but in non-LTE, you have only one element at a time. That's a limitation. So you can have one element in non-LTE plus how many you want in LTE.
But you have to do more than one atom at the same time.
Right.
That's not funny.
Yeah. It could be done. It's just, you know, it will take coding.
Yeah.
I just have one comment about the 3D record transport. This has a long history of varieties. Actually, me and a bunch of others just submitted papers with this on it. If you get down below about photon mean free path, very interesting things happen. And actually, the HST is designed to look down at the sort of levels at which magnetic field starts to diffuse across the plasma or vice versa in the atmosphere. And that's the real interesting physics I think in the photosphere that will come out of HST. And so I reckon if you blew up one of those boxes, I mean the HST is going to have 0.03 arcsecond resolution or something. On that scale, that's you've got 16 arcseconds there. So if you really looked in great detail, I think you have to handle a 3D problem. If you have scattering in a force function or what. So you'll come straight down to what it is. So what I'm saying is I think you have to go to 3D. Still. So
Maybe,
it
yeah.
depends what you want, but if the question you're asking is what is the interaction of magnetic field with convection, then I think you may get some answers out of a 1D column by column analysis that you're doing here. But I think at the end of the day you're going to have to deal with the fact that photons trying to escape radially, but sometimes they escape laterally and then come out. So I think that kind of thing is going to be important.
I think it is the nail on the head that all these things, this question of does it work, to me, there is any concern with that. Are we going to learn something from? And I think we will only when we have focused ourselves on the physical question.
Yeah.
And then you know exactly what corners you're cutting the difference and what others you can't cut.
Yeah.
So I think solar physics nowadays can be very daunting for me. When I look at all these complicated observations, so complicated, I need a leading question for four stars to get to.
Yep.
So I kind of great difficulty with in the optical school, the things that nothing can be understood, everything that you can know. But it's a good place to start. You know? So those questions are wonderful. So does it work? Well, does it work at that level? You're talking about technicalities of the model. Does it really work as a sort of goal? Maybe like identify something.
No, I agree with you. The answer always should be depends what your problem is, right? Yeah. Depends what your problem is.
So I love it when you get something that directly complicates.
That's painful, but
Something complicated.
Yeah.
Brazil 1-7. I mean,
I think it's painful in a remarkable way. Typically, you avoid the contradiction. You know, it's like you didn't learn your basics in your textbook, and you need it for your work, but you keep ignoring it. It's very painful when you do it. Until finally, you know you've got to cross the bridge. That's when you sit down for 2 hours and actually finally learn something new. So I think those things sort of lead you to such a problem.
speaking of this, you wrote B as curl of A, would you even have the question of everything?
Yeah, but then you pay a price when you do that. So you never get something for nothing. But as long
Unless
as
you use a
know,
credit
as long as
card.
you know that the bookkeeping is giving you problems. So there was something else that struck me. Hector, you're saying that we don't know. So I felt that not knowing or knowing that it's not working is so bad. As long as you know it's not working, it's terribly bad when you don't even know that it's not working.
Yes, yes.
I've worked in that area for decades. I mean, what's wrong with that?
There's a famous quote by Donald Rumsfeld where he said, "There's things that we know, and there's things that we know we don't know. The really scary things are the things that we don't know we don't know."
And then he gets confused.
It's not really him or Groucho Marx.
Well, I heard from him. But
Just out of curiosity, how many hours of effort have actually gone into this work?
oh,
It's kind of strange.
I'll need to write a code to answer that question. I think, ever since I started my thesis, even part-time, I've always been working on this in a way. So, yeah. This is, I'm sure these are, if you were to put this in what do you call this, man-hour, no. I've done most, but like I said, those guys have helped me a lot. Jaime, Andres, Javier, and Vasily. Yes. But it's been years of effort.
Doesn't it bother you that if it's high resolution, say you identify different places on the sun, you have to then keep track of the environment of these features because the environment is going to affect the features.
Yeah. Yeah, and that's why we need these observations, with a field of view that is not just one single slit. And we need the context. We need to see what happened before, what happened after. So that's why we need so much data. I
You're
agree.
assuming that you made a comment that the observation basically spectrally involved.
Yeah.
So basically, are there instruments now? Are there instruments available now that can
Provide this kind of observations. There's not very many now, but we have a lot coming up. I mean, with ATST, I still like to call it ATST, and Solar C, and
so that's a warning in terms of these. Really, this NICOLE is not going to be appropriate for other data sets. There's an assumption that goes into being able to.
yeah. Well, and again, we go back to BC's comment. I mean, it depends what your question is. Yeah. I've applied NICOLE to Atlas observations, right? So it depends what you're asking of it. So I've used it for abundance studies, for example, and you can do that. You can take a 3D model, compute profiles, average them, and compare that to spatially average profiles, that sort of things. So it depends on your problem. Yes.
Interfacing with NICOLE.
Oh.
It seems like you presented NICOLE in the context of chromospheric inversion. It seems like you could apply photosphere, anything the same on or hyper.
Mm-hmm.
But each instrument has its own data format, expecting a hypercube detection in NICOLE.
Mm-hmm.
What kind of assistance do you provide in your 84 pages for those of us who might have, say, 4 polarimeters coming online here in the next 3 years, so that we can interface to NICOLE?
Yeah. So there's several options. You can decide that you want to write your data in NICOLE's binary format. You can do that. Or, like I said, another option, NICOLE reads IDL files. So there's a bunch of IDL routines that you can use to write files in NICOLE's format, or convert files between IDL and NICOLE, or just if you put your if you create some IDL variables that NICOLE expects, like I is an array with x, y, lambda, q, u, and v the same, then you can just write a save file and NICOLE will digest it.
Save file.
Mm-hmm.
Then NICOLE would require a fair amount of metadata for your observation.
Yes.
So
That goes in the configuration file.
same kind of thing.
So you have a configuration file. It's an ASCII file where you say there's 3 spectral regions. The first region starts at 6,000 angstroms. The spectral sampling is 25 milliangstroms, and I have 4 wavelengths here. That sort of stuff.
So for a given instrument, we need to have a tool that can turn whatever comes off to polarimeter.
Yeah. Or if your instrument always spits the data in the same format, then you can have a configuration file for NICOLE that will just read that format. Yeah, I've thought about it, yeah. But then I will have to add some additional libraries.
I mean, it has to come from both sides because you cannot do a code that reads absolutely everything.
Yeah.
I know one big telescope started falling off that bridge.
What's wrong with this?
Nothing wrong. Yeah, I could have it too. Yeah. Volunteer to.
I've not experimented myself, but I think that would be true on a scale of like HMI, not on a scale. I mean, there's going to be a lot of data, but it's I don't know. Yeah. There's going to be a lot of it. Yeah. There's a lot of it. I mean, when you think about pipeline, yeah, that is true. It's just like the proposal was one of everybody's got to write a formatter at some point. It's just such a confusion because of the size of the team. Right? Any other questions?
Well, I have one more thing to say. Since we talked about 1999 when I first came to HAO, I remember that the very first day I arrived here, Tom Bogdan took me out for dinner with some other people he was able to recruit from HAO. He took me to the Black Cat downtown. And amazingly, there's one person sitting in this room who was at that dinner 15 years ago. Hi, Alice. So, thank you all. It's been great to see you all again, and yeah, I hope to come back more.
Oh, just before everybody leaves, next week's colloquium is going to be at 10:30 a.m.
I have to run now.
Okay.
But I'll see you later in the week. I've got to go back and finish laying the floor. I'll make sure I put the TV on.
Yes, I
Did
was.
you watch any of the US games?
Yeah, I watched the one they lost actually. Was it?
But the US was good. I mean,
Yeah,
much better
I like
than
them.
England for God's
I was rooting for them and for Costa Rica.
sake. Yeah, oh, I know. I would have loved
Yeah,
it.
England's like. Yeah, you were rooting for them too.